Alrighty, in this video we're going over something called quantiles, which is a very fancy way of saying inverse normal, and it should actually hopefully be a revision from what we've done in year 11. Okay, so let's draw a picture of this situation. X is normally distributed. It's got a mean of 23.6 and a standard deviation of 3.1. So 23.6, standard deviation of 3.1. So the next one would be 26.7, and the one before it should be 20.5. And you could sort of keep going out like that, drawing out your standard deviations. We want to find out a k-value, so let's just put it out like here or something. And then I want the probability that we're less than k to be 0.95. So that whole yellow area, 0.95 should be the area there. So that's a question we're asking with this. So what we're going to do is we'll go into our normal distribution. Now, if you're on a Texas, it's going to look very similar. Go to where you'd normally find normal CDF and do inverse normal. So what we need is a left tail, because you can see that I've sort of shaded into the left. So if we got something like that is a left, but if we got something like that would be a right tail. So you have to maybe draw a picture and just figure out which one you want. So we want a left tail here. The area is 0.95. The standard deviation was 3.1. And the mean was 23.6. All right, so we're going to execute that. 28.699 is our k-value. Now, time for a sanity check. Does it look like 28 should be about where that k-value is? Well, yeah, 23, 26, 28 kind of makes sense. That's good. Now, the other thing I will mention is you can also do this if you flip the tail. So if you did do a right tail for whatever reason, the area to the right of that tail just should be 0.05. Now, if you do that, it will still work. So 28.699. So you got to be really careful, because on some older calculators, you're only allowed to do left tails. So you have to keep that in mind when you're working with inverse normals. All right, next we're going to do this. The reaction time of 17-year-olds are normally distributed like that. Find the reaction time you need to be in the fastest 10% of 17-year-olds. So we want the fastest 10%. We want reaction time. So we'd be looking something like this. They're distributed with a mean of 0.25 and standard deviation of 0.2. So actually that should be 0.02, my bad. So you get 0.27 as your next one, and 0.23. And basically you want to figure out what number do you need. So let's call that K again, so that you're in the fastest 10%. So that area should be 0.1 there. So again, we're going to go to this inverse normal situation. On a Texas, it is where you just find normal CDF. On the Casio, it's here, inverse normal. We're going to be doing that left tail there. The area is going to be 0.1, because that's 10%. Standard deviation is going to be 0.02, and the mean is going to be 0.25 seconds. There we go. We're going to hit execute there, and then it's 0.224. So K equals 0.224. So you could have a sentence there. If your reaction time is 0.24 seconds or less, then you are in the top 10%, something like that for the interpretation. All right, great. Question 3, the weights of an adult scallop, blah, blah, blah. We want to find the mean weight. Now, this should actually be a flashback to what we did with Z distributions. The reason I'm covering this again is because, well, it's hard to find these unknown means. So we'll use this as a little opportunity, because it is very related to inverse normals. So that's going to be Z equals X take mu over sigma. And then we got to draw a picture. Always draw a picture. So 15% of the scallops weigh less than 58.2. I'll stress we're seeing a lot of left tails here, but it can come up that we have right tails. So this is 58.2, and this area here is 0.15. And then we want to know what the mean, but that's actually sort of unknown at the moment. But we do know the standard deviation is 5.9. I need to figure out the equivalent Z score of that. So to get my Z score, we're going to do inverse normal. So the area is 0.15, the mean will be 0, and the standard deviation will be 1. So let's do that. So left tail, 0.15. The standard deviation is 1, and the mean is 0. Hit execute, and the Z score we want is minus 1.036. Great. And then we can just plug all this into our equation. So z equals x take mu over sigma. So that's minus 1.036 equals the x value as our observation, 58.2. Take our unknown mean over the standard deviation. Standard deviation is, where is it? 5.9. And this is just something that I can solve. Okay, so let's times 5.9 by both sides. So 58.2 minus the mean equals minus 1.036 times 5.9. And then I can sort of keep shuffling this, so I can maybe move the mean over here. Mean take 1.036 times 5.9 equals 58.2. And then the mean actually is 58.2 plus 1.036 times 5.9. We'll just see what that is. So we're going to exit back to our menu, do this. 58.2 plus 1.036 times 5.9 gives you 64.3124. All right, now you can actually put units on this as well, so that's in grams. And then if we want to double check that, we can calculate the probability that x is less than 58.2. Suppose x is distributed normally with a mean of 64.3124 and a standard deviation, which was 5.9. We'd want to maybe calculate the probability that x is less than 58.2, which is roughly, well, it should be exactly 15% if we've done everything right. So let's just check that. Stats, distribution, normal, NCD. Lower is minus a whole bunch of 9s. Upper is 58.2. The mean standard deviation is going to be 5.9. The mean is going to be 64.3124. Execute that, and we should get exactly 15%, or at least close enough. The reason it's not exact is because we have rounded that mean before we've used it in our calculation. So 0.15, we are very happy indeed because we got it right. Now, I'll stress that some questions you don't know the standard deviation. That's just a different rearrangement. And other questions where you don't know the mean and the standard deviation, you will get 2 equations and 2 unknowns. You have to solve those simultaneously. So just be aware of that.